All right, so in this video, I would like to talk about one of the applications of derivatives, which is optimization. Great tool for finding maximums and minimums of quantity of interest. Here, what I want to look at, I want to look at a very geometric question. What's the largest rectangle that can be inscribed in a quarter circle? And I'm going to assume it's a unit quarter circle, since the answer will be the same, just scaled proportionally. So for simplicity, let's pick a unit circle. And I want to say, you can imagine if you pick a rectangle that's too too short, right? It's not going to have, and when I say largest, I mean by area, largest by area, right? So if you pick a rectangle that's too short, it's not going to have very much area because it's too thin, right? And if you pick one similarly that's too tall, it'll be too skinny, right? And won't have much area. So, but where is that sweet spot of, do you get the biggest possible area? Is it for a square, or is it, I don't know, maybe you get a bigger one with that, I don't know, golden ratio between the sides or something, right? What is that best possible area that you can get in a rectangle? So to accomplish this, what I'm going to do is I'm going to give labels to all the dimensions. So let's call x the width of the rectangle. So then I can say what the height of the rectangle is. Y equals square root of 1 minus x squared, just solving the circle equation for y. Is all we're doing there. And then we can draw our actual rectangle. That is really not a 90-degree angle. There we go, close enough. So the area then is just height times width because it's a rectangle. But I want it all in terms of x, right? So our function that we wish to optimize is a of x equals x times y, but y is 1 minus x squared, right? Note that this problem is guaranteed to have a solution because this function is continuous on the domain of all plausible x values. Here, I really can only use x values between 0 and 1 because I can't pick the width of the rectangle to be less than 0. I can't pick the width of the rectangle to be more than 1. And this function is perfectly continuous on 0, 1. Therefore, it's continuous on a closed interval. So by the extreme value theorem, it has absolute max and absolute mins on that interval, right? So it again, extreme value theorem doesn't tell you how to find them, but note that here it does promise that they exist. So that's nice. At least we know the problem has a solution. Now let's go use derivatives to try to find it. So this is our function, x times square root of 1 minus x squared. And I'd like to find the max of it, right? The biggest possible area. So all I'm going to do now is I'm going to use Fermat's theorem, right? So Fermat's theorem says that extrema must occur at a endpoint or critical point. Here, the endpoints I know are definitely not going to be maximum because at the endpoint, the rectangle has area 0, right? So here I really want to know where is the derivative? 0. That's the equation I want to solve. So let's calculate that derivative. Notice we need a chain rule here, right? So I do the derivative of the first times the second plus the first times the derivative of the second. Those 2's cancel. And I can also multiply the top and bottom of this first expression by square root of 1 minus x squared, because I want to come to the denominator. Now I can add the fractions. And this is 0 if and only if the numerator is 0. Because it's a fraction. The fractions are 0 only when the numerator is 0. So now 1 minus 2x squared equals 0. That's actually easy to solve. Just add the 2x squared, divide by 2, divide by 2. There is our x value. Notice when I took a square root, I didn't put plus or minus, because only the positive value makes sense here, right? The negative x wouldn't be in the domain. Right, this is x equals 0, this is x equals 1. So what did I get? I got square root of 2 over 2 for x, right? That's the x value. Now, what's interesting here what's interesting here is then computing the corresponding y value. Right, we're getting x is root over 2 over 2. Well, then you can calculate the y value by plugging into the formula. Or you don't have to plug into the formula. This is a unit circle. So you can just say when x is root 2 over 2 on the unit circle, that's actually a famous point on the unit circle, right? Y is also root 2 over 2. So that is the biggest possible rectangle. Basically is a root 2 over 2 by root 2 over 2 square. Right. So on that circle, that's the biggest right? The biggest possible rectangle we can get is, pardon my less than perfect drawing, right? So this is a root 2 over 2 by root 2 over 2 square. Right. That's the biggest possible rectangle we can inscribe in this circle. All right, great. Thank you for watching. There's our little optimization application with derivatives.